quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
The double-slit experiment is based on the wave-particle duality of subatomic particles. As simple a concept as it is, it produces some of the most astonishing experimental results of quantum mechanics. This experiment stands at the heart of quantum weirdness because it is one of the strangest things in science. Shooting classical particles, that is, small balls of matter, at a screen with a single slit in it, produces a simple spray of particles on the second screen behind it. When a wave passes through a single slit, it produces a similar pattern. That is, a bright spot in the center that dims as one moves away from the center. When you add a second slit to the first screen, classical particles would tend to form two sprays of particles on the second screen. When you add a second slit to the first screen, a wave forms a series of several light and dark stripes, as shown below. Shooting quantum particles, that is, subatomic particles, at a screen with a single slit in it, produces a simple spray of particles on the second screen behind it. So far, so good. This result is actually consistent with both waves and particles. Now, this is where it starts getting strange. Shooting quantum particles at a screen with two slits in it, one would expect them to form two sprays of particles on the second screen. However, when one actually shoots quantum particles at a screen with two slits in it, like a wave, quantum particles form a series of several light and dark strips. This shows the wave nature of quantum particles. As strange as this is, the quantum world gets even stranger. One possibility that was considered is that the quantum particles are somehow interacting with each other to form the series of several light and dark strips. The solution was to shoot the particles one at a time so that they cannot interact. Here are the results of a double-slit experiment showing the buildup of an interference pattern of 100 single electrons. Here is the result of a double-slit experiment showing the buildup of an interference pattern of 3,000 single electrons. Here are the results of a double-slit experiment showing the buildup of an interference pattern of 20,000 individual electrons. Here are the results of a double-slit experiment showing the buildup of an interference pattern of 700,000 individual electrons. Note that the electrons still form an interference pattern, even when shot one at a time. This shows that the wave nature of subatomic particles is inherent in each particle. These results actually seem to require each electron to go through both slits at the same time. However, quantum mechanical strangeness still gets even stranger. The notion of one particle going through both slits at the same time is so anti-intuitive that physicists had to look to see which slit each particle is actually going through. So to look, experimenters put detectors by the slit so as to look to see which slit each particle actually went through. The results were that the subatomic particles formed a spray line behind each slit, just like classical particles would. This suggested the electrons somehow knew that they were being watched. And this is not the end of the strangeness, because it's about to get even stranger. Suspecting the detectors were causing the difference, the experimenters turned off the recorder while leaving the detectors on. However, this time they got the interference pattern. Experimenters have even had the recorder on, but with the tape removed while leaving the detectors on. They still got the interference pattern. The fact was that the subatomic particles only produced the double line when the information about them was actually being recorded. So it is the act of observing that affects the experiment, and not the measuring devices themselves. Quantum eraser experiments are a new set of double-slit experiments that closes the gap. These experiments eliminate many possible explanations for what is going on. What follows is based on the paper Double-Slit Quantum Erasure, published in Physical Review on February 20th, 2002. Warning, what follows may blow your mind. The experiment uses single photons from an argon ion pump laser at a wavelength of 351.1 nanometers. The photons pass through a special nonlinear crystal called beta barium formate, labeled here as BBO. It is used to produce entangled photon pairs, each with twice the original wavelength, giving them a wavelength of 702.2 nanometers. Each photon goes in a different direction, shown by the labels P and S, and the photons go to two different detectors. The S photons go to detector DS, and the P photons go to detector DP. Detector DS provides both the position and polarization of the S photons. Detector DP provides the polarization of the P photons. This information is then recorded by a recording device. The gray line labeled S-DS is the point along the P photon path that is the same distance as is traveled by the S photon to DS. Note that at this point, dP is before S-DS, such that P photons are detected before the S photons are detected. Placing a double slit in the path of the S photons produces the interference pattern of the classical double slit experiment. However, as before, this is where things start getting strange. Quarter wave plates, labeled here as QWP, are special crystals that change linearly polarized light into circularly polarized light. In this case, there are two quarter wave plates. For a photon of a given linear polarization, one plate changes it to right circular polarization, and the other changes it to left circular polarization. Since the S and P photons are entangled, knowing the polarization of the P photon allows us to know the original polarization of the S photon. Placing these quarter wave plates in front of each slit makes it possible to figure out which slit the S photon went through without disturbing it. As a result, we get the double peak pattern instead of the interference pattern. Now, since the QWPs don't disturb the S photon, it proves that the detectors are not what changes the result of the experiment. Placing a polarizer in the path of the P photon destroys our information that tells us the S photon's original polarization. As a result, it is no longer possible to know which slit the S photon went through. The result is that the interference pattern comes back. Now, if you still have any working neurons left, what comes next will probably fry what's left. Delayed erasure erases the P photon polarization after the S photon is detected. Extending the P photon's distance to dP to beyond the S photon's distance to S without the QWPs, we get the interference pattern. When the QWPs are put back into place, the interference pattern is once again lost, producing the double peak pattern again. Now, placing the polarizer in the path of the P photon after the distance that the S photon travels to the S, that is S-DS, what would we expect to see? Common sense suggests that since the S photon is detected before the P photon's polarization information is destroyed, that we should get the double peak pattern. However, the result is the interference pattern again. So what we have here is that the QWP form a measuring system that tags the S photons without disturbing them. And additional information is needed from the P photon to determine which slit the S photon came through. When that information is measured, the tagged photons form a double P pattern. On the other hand, when this information is destroyed, the tagged photons form an interference pattern. In each case, the tagging QWPs are in place. The DP and DS detectors are detecting the P and S photons respectively. The information from both sets of detectors is sent to a recorder and actually recorded. The same results occur whether or not the P photon information is destroyed before or after the S photon is detected. This prevents the S photon from being affected by the change in the P photon due to entanglement. When the results of this experiment are analyzed, the only real change is in the content of the information being measured and recorded. In one case, the information allows one to find out which slit the S photon went through. In the other case, the information does not allow one to find out which slit the S photon went through. This shows that the determining factor is the information. It is the information about an event that causes wave function collapse or decoherence, if you prefer. So what is really happening? In general, the wave function represents multiple possibilities. When specific information is measured about an event, those possibilities are reduced to one, producing the needed information. It then produces a new wave function of multiple possibilities consistent with that one possibility. All of this put together indicates that what we call reality is immaterial at its most fundamental level. At its most fundamental level, the universe seems to be composed entirely of information. This makes it more like a sophisticated computer program than a world of material objects. It is not just the existence of the information, but its ability to eventually be accessed by an observer. That observer is ultimately a conscious entity. The information that makes up reality seems to be calculated as needed for a conscious entity so as to produce a consistent reality. One thing this does show is that consciousness is a fundamental part of reality. This is not New Age thought, but what the observation of subatomic particles is actually telling us. It is also consistent with the biblical view of God as creator, since the universe would be a result of his consciousness. It is also consistent with the biblical view of God creating the universe out of nothing. The double slit experiment is based on the wave-particle duality of subatomic particles. As simple a concept as it is,
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave.
QuantumLaserPointers.com.
Not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers. QuantumLaserPointers.com.
A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits